Okay, moving on with circuit protection devices part 2. And we're going to be looking at HRC fuses, or otherwise known as high rupturing capacity fuses. So high rupturing capacity fuses. Essentially, the biggest advantage here, and I have talked about this before, is that the prospective short circuit current, or the maximum breaking capacity of an HRC, is much higher than any other MCB or fuse that we have available. You'll remember that the construction of these is essentially a fuse element inside that ceramic casing, which then has sand, basically. Let's just say sand inside it. That quenches the arc, that keeps it down to a minimum, any potential for arcing or explosion to come out. And then just the very highly calibrated element inside there will blow, and they can calibrate these things really accurately. If you haven't already, what I would recommend is that you go and have a look at the other YouTube videos on the Canvas page for this topic. Some really good videos there about a couple in particular about HRC fuses. They have some, there's one in particular, or a couple that show devices operate, and one in particular that shows the HRC blowing with two side by side of varying qualities, which shows you the difference and what can go wrong in terms of that rupturing capacity. So, explodes into bits kind of thing. So the information here, I've said that before, the high prospective short circuit currents is really the primary value of an HRC fuse. The labels on it, the fuse itself will have labels on it, and that identify the voltage, current, breaking capacity, and the certification. So old classes of high rupturing capacity fuses. So these are this is the classes of HRC fuses prior to 1998 rather. So these are the indicators, or the codes that you'll find on the HRC fuse, and this is what they mean. Are we going to see HRC fuses that are more than 22 years old? Yeah, actually, I think you probably will. You probably will come across these from time to time. Most cases, 1998, those things are getting pretty old, right? So most of them will be replaced. But on the other hand, it's entirely possible that you've got stuff that a fuse was installed when the building was first wired up, and it's never been changed since. So in that case, you probably will find some quite old stuff. So I won't read through this. You can do that. Be aware of the coarse and close protection and that fusing factor. Remember, our fusing factor is the rated current divided by, or maximum. So let's try that again. The minimum fusing current, the minimum current at which it will fuse, divided by the maximum current that it will fuse at, or the maximum current that it's going to withstand. So that is our window of the lowest up to the highest currents that it will either break or withstand. So the higher that number there, the bigger that window. So it's less accurate, which is why we've got those high numbers there, say coarse protection. And we're using those generally, that coarse protection, for motor rating. Remember that we have, this is important through the whole, to remember through this whole topic, so I'll talk about it now, but motors will always draw a fairly high startup current, depending on the size of the motor, of course, but typically I believe in the order of 6 times the running current. That is what it is. There's nothing that we can do about it. What we don't want there, what we need to maintain is obviously circuit protection for those motors. What we don't want to do is have circuit protection that will trip every time we start the motor because it sees 6 times the current and it goes, nah, we're turning off. So we need to have a particular type of protection for motors. When we talk about circuit breakers, that's where we have that B, C, and D class of the breakers. So the the D class trip more slowly than the A, B, C. So they will see that high current and they'll want to trip, but because they trip more slowly, then by the time it gets around to tripping, that current has disappeared again. Because we'll only see that high startup current for a motor for like less than a second, actually a lot less than a second. If you tried to measure it on your ammeter, you wouldn't be able to see it. The ammeter is not going to move fast enough for you to be able to even see that. So it's way less than a second. So we have to use some sort of course protection. And in this case here, that means that when we have small overloads, then they're unlikely to trip. They're way less likely to trip. So we just have to be careful there with our motor rated applications. But you'll see these things, and you'll see these HRCs, and you'll actually see them marked as and referred to as motor rated fuses. So you can get different types of fuses. A motor rated fuse is one that will withstand a higher current for a bit longer. All right. Okay, so then the new terminology, so since 1998 for HRC fuses. Utilization category is the term that replaced the concept of fusing factor. So we don't talk too much about fusing factor anymore, which is fusing factor being that ratio of minimum to maximum tripping current, or fusing current. It's a combination of specified requirements related to the conditions in which the fuse link fulfills its purpose, selected to represent a characteristic group of applications. Interrupting capacity and utilization category for newer type HRC fuses can be identified by the symbols GG, GL, GM, AM, GD, GN, etc. that are printed on the fuse barrel or the fuse label, or stamped on the metal end caps on the fuse. So these codes will be on the fuse itself. The first letter in lowercase of the symbol indicates the interrupting capacity of the fuse. A G, so a lowercase g, means it has a full range breaking capacity. A means that it has a partial breaking capacity. The second letter in capitals indicates the utilization category, defining the accuracy for time current characteristics, conventional times and currents and gates. G or L both indicate for general. M is for motor. D is a time delay. N is a non-time delay. Okay, so identification of those labeling. So a GG or a GL, that's being a full range breaking capacity with general applications. So operating characteristic range is 1.2 to 1.6, so 120 to 160% of the fusing current range. That's where it's going to trip. So if I get a 10 amp fuse that is a GG or a GL, it's going to blow somewhere between 1.2 and 1.6. So this is where, like we said, the fusing factor before would be that minimum to maximum. Now we're just talking about that characteristic range. So our minimum then is going to be 1.2, maximum will be 1.6. The GM, so the G being the same as above, M being motor rated. So our typical operating characteristic range is going to be above 1.6 and generally between 1.7 and 2.5, so 170 to 250% of the fuse current rating. So these ones are less accurate because we need to give them that, we need to give the motor that ability to draw that high startup current. So we don't want to use these for general purpose because they're going to trip more slowly. In fact, that it's going to take somewhere between 1.7 and 2.5 times the fuse rated current for it to trip. So on a 10 amp fuse, it's going to be 17 to 25 amps before it actually blows. Again, that is specifically for motors because of that high startup current. Labeling on older type HRC fuses in existing installations. Many installations will have HRC fuse links that were manufactured prior to 1998 or existing switchboards loaded with fuses labeled Class P, Class Q1, Class 2, Q2 or Class R. These classes represent fusing factor. Fusing factor is the ratio of minimum fusing current to the rated current of a fuse. It often appeared as on the label as FF, followed by a class, a letter, and then a number. For example, FF class Q1. So this is where, as I said before, if we go into buildings that may have the same fuses in there that were installed originally, we may come across these older type ones. So an example would be an older type HRC fuse has the following information: 20 amp AC44550V class Q1. What does it mean? 20 amp, that's the fuse current rating. Fuse current rating. AC44 is the short circuit breaking capacity, so that's 44,000 amps, and also known as category of duty. So heaps, right? And remember that our HRC fuses, that's what they're called, right? High rupturing capacity. So they're good for breaking big short circuit currents. 550 would be the voltage. 550V means 550 volts maximum. And class Q1 has a fusing factor between 1.25 and 1.5. So this is a newer one, a newer fuse. You can see the ratings on here. We've got AC 550V, 80kA, 100 amps written there, and GG/Q1. So AC 550 volts means the maximum voltage of the fuse is 550 volts. AC 80. AC 80. Where does it say AC 80? It doesn't. It says there 80kA, which is the same as AC 80. So this is the maximum fault current, the category of duty, 80,000 amps, 80kA. GG is our fusing factor, 1.2 to 1.6. It also says /Q1, so it's got a reference there to the old ratings. So we've got a GG and a Q1. If we go back to the previous slide, we'll see that Q1 there had the fusing factor between 1.25 and 1.5. So this one says 1.2 to 1.6, so they're roughly equivalent. The GG is equivalent to the old Q1. And then 100 amps there. The maximum current the fuse can continuously carry without overheating and causing deterioration. So that's our fuse rating. That's our fuse rating. It's a 100 amp fuse. Okay, HRC fuse operation. What do we got there? Well, you guys can read that, and I will talk about, in layman's terms, what's happening. We have kind of like a metal plate inside the fuse itself with multiple small joints. And again, go to the videos on the Canvas page if you haven't already. There's a really good one that actually talks about the operation of the fuse, how an HRC fuse operates, and it's kind of like a metal plate with lots of little joints. And in fact, I won't talk about this any further. Go and watch that video. It's a good one. None of the videos on this topic are more than about 3 minutes. So just go and have a look at that, and it'll tell you how the heat produced by a high current will break down the fusing element. So the basics of it, however, are large current flows. An arc is produced. The heat produced causes fusion between the fuse element vapor and the silica powder, and that's the sand inside. Arc energy is absorbed to produce a highly insulating silicate compound. The arc is extinguished. Current flow ceases. The circuit is safely interrupted. Clearance time. HRC fuse is designed to safely interrupt a high value of short circuit current and to withstand without damage the high values of energy associated with short circuits for as long as it takes to open the circuit. The total time for any fuse to operate and clear a fault is called the total clearance or total operating time. It consists of pre-arcing time plus arcing time. Pre-arcing time is the time taken from the instant a current is large enough to melt the fuse till the instant that the arc is initiated. Remember, so what we're talking about there, if we think about this as our fuse, so the pre-arcing time is, okay, go. We've got our current flowing, our very high current, and then the arc is initiated when my fuse starts to break. Now that I've got a gap there, I'm going to have an arc in the middle. And then as it gets further and further apart, because my fuse element is starting to become destroyed, then that's our arcing time. So the pre-arcing time is the time from that high current flowing till my arc is initiated, which is the separation of the fuse element. So I guess the pre-arcing ends when the fuse element begins to vaporize. Arcing time is the time taken from the instant of initiation of the arc to the instant of final extinction. When the available fault current is high compared to the rating of the fuse link operates in a very short period of time, typically less than half a cycle. So that would be like, 10 milliseconds. Prevents current from actually reaching the peak value on the sine wave. So if half a cycle is one peak, we want it to be less than that, because then it stops it if it's stopping it on the way up, then we're not even going to get the full current. We're not even going to get the full current flow. So as I said, our pre-arcing time is the time from when the current starts to flow until my fuse link starts to separate. Arcing time is when my fuse link is being destroyed, so the gap is getting bigger and bigger. The arc is across the middle, and when my gap becomes big enough that the arc is extinguished, assisted by the process of the quartz quenching the arc, then once that arc is extinguished, then current flow has ceased. So our arcing time is the time from when arcing begins until the fuse is effectively killed the circuit. So our total time, the total clearance time, is then the time from the instant that high current starts to flow until no current is flowing again. Okay, so the characteristic for the HRC, a figure above shows current being limited to around half the available peak fault current. So within the first quarter of the waveform. So remember, 1/4 of our waveform will be our positive peak, right? So it's 1/4, then our halfway point will be where we reach 0, 3/4 will be our negative peak, and then a full waveform will be back to 0 again. The pre-arcing time is lengthened by heat loss from the fuse element. The arcing time is generally limited to no longer than the first or second voltage 0 in the sine wave after arcing begins. Assumes that the start of fault current occurs exactly when the sine wave current is passing through at 0 point. So there's an assumption there that this is the point where our high current starts, and then we're going up here. But it could be anywhere, right? The sine wave could be here when our high current starts. But we have to assume something. This is called a symmetrical fault current. Cool. Time current characteristics. When a fault causes a high current to flow, the higher the current, the quicker the protection device will operate. As current through the protection device increases, its operating time decreases. This is called the inverse time current. We've talked about this. The thing that we need to remember is, as the fault current increases, then the time it takes for the device to operate comes down. This is typical of every kind of device, not just an HRC fuse. Would be a circuit breaker or anything. Okay, close and coarse protection. Let's talk about that. GG and GL type fuse links are for general purpose applications. They have a current rating equal to or less than the cable current rating, providing protection against sustained overloads and short circuits. They provide close excess current protection. So this means that the close excess current protection means that, remember that specific definition is 1. They'll blow within 4 hours at 1.5 times the rated current. So this is our normal type of circuit protection that we would use. A GM type fuse link is designed with a time delay to withstand motor inrush current surges of up to 7 times full load current. So I said before 6 times, this is 7 times, somewhere in that region, right? So that's our short startup current, a short term or very short period high startup current on a motor. So a GM type fuse link is a coarse excess current protection. Because we are putting that essentially a time delay on it, that pushes out all of our tripping time. So on a normal overload, it's going to take a little bit longer to trip, which means only coarse protection. So it's not ideal for protecting cables and protecting fittings. So one little thing that's interesting here worth noting, we're talking about direct online starting. Now, if you paid careful attention in the control circuits topic, you'll remember that a direct online starter is just where I push a start button, it energizes the coil pulls in contacts, current flows to our load, in this case a motor, which is fairly typical, and that's a reasonably standard type of starter. In fact, the most common starter for the vast majority of motors, and the vast majority of time that gives us no problem. There are such things as soft starters. I think I've talked about this before, where we might control the voltage or even the frequency going to that motor in order to slowly ramp it up. I've talked about that in terms of minimizing our mechanical stress on things. Like if I've got a motor that's powering a big conveyor belt production line, something like that, I don't want that motor to try and go from 0 to full speed in an instant, because everything else on that everything that's mechanically connected to that motor is then just going to get a big shock as it goes, and I will start to reduce the life of all of those components because of that mechanical stress. But in terms of our fusing and protection, there's also value there, right? Because if I start this, if I do what's called a soft start, so we slowly ramp the speed up, maybe only over 5 to 10 seconds, then we're also going to reduce that startup current on the motor, and that way we could have closer protection. We don't need to worry so much about that startup current or inrush current. Okay, here's a little table here comparing the different codes for of the old and new types. So this here tells us GG or GL, which is our generals. They replace class Q1, which we saw previously. So it's talking about the operating characteristic ranges, the rupturing capacity or braking capacity. Yeah, I won't talk through all of those. You can pause the video and have a read of that. Miniature circuit breaker, MCBs. All right, I will take a pause here. We will stop this video. The second number of your access code is 4. So the second number on your access code for the video will be 4. See you again soon.